Okay, I guess we can start. So today is our fourth class. Do you remember what we did in our last class? Orthogonal trajectories, right? Okay. Some of you may think that when we were trying to construct the ordinary differential equations from the equation of the family of curves, you may be thinking that the way we constructed the differential equation, it holds only when we are trying to find out orthogonal trajectories. But that is not the case. Whenever you want to construct some differential equation out of some given relations, the methodology is the same, that you have to, eliminate the parameter present in that equation. Okay, fine. So as promised, so today I'm going to start initial value problem. Initial value problem. Okay, in short, it is called IVP. Okay, so you must have seen it already. Like as I was talking about, like say I may define implicitly a differential equation of nth order in this way. In this way, okay? But what I'm going to do here, I would like to explicitly express the nth order derivative in terms of the other arguments here, so that I'll be able to impose the conditions associated with this differential equation. Okay, so that is why rather than writing in this form, let us try to write this in this form, you know, where your y is the dependent variable and x of course is the independent variable. So I can write it as what? Can somebody tell me?
N minus 1. N minus 1.
Yes, it is the n minus 1th order derivative here. Okay, so now if I want to solve this differential equation, like say I may get some mathematical expression, but you know that while I'm going to solve it, then it is going to give me one n parameter family of curves, right? Now, if I'm trying to seek some particular solution or particular integral out of this differential equation, I must be given some conditions. Okay, I must be given some conditions. Okay, and those conditions, they will be called, initial conditions. So basically, what we will try to do, we are going to try to solve this differential equation, your subject to initial conditions, subject to initial conditions. The first thing is your and so on, and eventually something like this. Okay, everything is clear?
Yes, sir.
Yes, sir.
Am I missing something here? Have I missed something here? Yes? Yes. Did I miss something?
Sir,
Yeah.
yn minus 1, I think. Last
one is yn minus 1. Okay, fine. I have corrected that. Apart from that, am I missing some information here? Or, is it that I haven't told you about something here? What is that?
There will be an interval where x naught belongs.
Yes. So firstly, about the interval of definition. Okay, let me call that as I. Okay, and of course, the hero of all these initial conditions, it is nothing but the point x naught, isn't it? I still haven't told you anything about the point x naught. Okay, so of course, this point x naught, it has to be defined in the interval of definition, say I. Okay, so basically, we are trying to solve this differential equation. Of course, this is an ODE, an order ODE, subject to these initial conditions. Okay, and when we say that it is initial condition, you shouldn't think that that point x naught, it is nothing but the very first point belonging to that interval. Okay, it can be any point on that interval, right? So I'll be more precise about this. So when I'm going to talk about first order and second order, differential equations, and then it will be more clear to you what could these conditions can represent. What could they represent here geometrically or physically? Okay, but remember, it may not be possible every time to interpret these conditions geometrically. Okay, only up to certain order we will be able to do it, and of course we would have to be given more auxiliary conditions in order to interpret everything geometrically or physically. Okay, fine. So that is why don't try to seek geometric interpretation. You would be able to, but the thing is that you if the differential equations, they come from some real life phenomena. Okay, so if you are mathematically modeling a real life phenomenon out of which these differential equations are coming from, so then you may be able to interpret all the initial conditions geometrically, but not every time. But for first order and second order, definitely we will be able to do that. Okay, so now let us see what formally we can do. So this is what you see in your slides. This is about initial value problems. So here, as I have told you, we are often interested in problems in which we seek a solution, yx, of a differential equation, so that yx satisfies some prescribed side conditions, that is, conditions imposed on the unknown yx or its derivatives on some interval I containing x naught. So this I have already told you. And so this is what you have to solve this differential equation 1 subject to these given conditions. Okay, and of course these are, remember, these y0 y1 up to yn minus 1. So these n entities, they are constants. They are constants, and of course they are specified real constants. Okay, and as I have told you, this is called an initial value problem, and the value of yx and its n minus 1 derivatives at a single point x naught, it is given by this, and they are called the initial conditions. Okay, it is as easy as that. It is as easy as that. Okay, so now what I'm going to do, I'm going to take you over to a first order differential equation, which is going to constitute an initial value problem. Okay, and you know that is going to be pretty straightforward. Okay, fine. So generally that one, right? Okay, so this is the first order differential equation, and then because this is the first order differential equation, so it is going to come up only with one initial condition. So that's it. It is going to define an initial value problem. Okay, and the physical interpretation of this is very simple. If say I is the interval of definition. See, so far I'm only talking about the interval of definition. I still haven't wrote in the extent of the graph of the function yx. Okay, I'll come back to that later on. Fine. So how we are going to interpret this? So basically, what we are trying to get, say, suppose this is my x-axis. And suppose this is y, where I am going to represent the function. And suppose this is, let us call it, say, AB. Suppose this closed interval AB, this closed interval, I'm considering a closed interval AB, and suppose the point x0 is here. Okay, so then I am seeking a solution curve. I am seeking a solution curve on this interval AB. Okay, so basically, so this is the point x0, and of course, if I rope in the y coordinate as well, so then this has to be the y coordinate has to be y0. Okay, fine. So I would like to rope in your that. Okay, so these are the first and second order initial problems. As you can see, it is very straightforward because you already know how you are going to define or how you are going to describe an initial problems for an nth order differential equation. This is pretty straightforward. So now here later on you are going to find another thing is that we are seeking solution in a rectangle R. In a rectangle R in R2. So you are going to come across this very frequently. You are going to come across this. So what is the meaning of that? See here, when we are trying to seek the solution in the interval AB, okay? So then suppose this pin graph, this is y equal to yx. Suppose this is the solution curve, right? Now what we are going to do, we are going to see the extent along the y-axis to which the solution curve can exist. Okay, so what we can do, like say we can seek one interval here which is going to incorporate the whole curve. Okay, so I can simply take another interval here, say C D. Okay, so then if I draw like this, so then if I use some shaded drawing here, so then this shaded rectangle, it is going to represent the region R, or it is called a rectangular region R. You will see that in Simon's book and in many other books. They are simply going to describe the initial problem in that rectangle R. Okay, now is it clear? This R, the concept of R. Okay, this is as easy as that. Okay, this is as easy. Yes, please.
Can you please repeat?
Okay, let me start from the beginning. Okay, see, firstly, whenever I'm going to talk about the initial value, right? So initial value, we are going to consider a fixed point in the interval of definition, right? That is x0. Okay, now, when I am trying to describe a first order, initial value problem, what I am seeking? I am seeking a solution curve passing through that particular point. Of course, when I am seeking a solution curve, of course, on that solution curve, this is nothing but the graph of a function, right? So all the points in that solution curve, it is going to have some coordinates like x, y. Okay, so that means corresponding to the point, x0, you are going to have a point y0, which has already been given by your initial condition, because y0 is nothing but the value of the function y at the point x0. Is it clear? Fine. So that means we are seeking a solution curve passing through the point x0, y0. Fine. Okay. So now you consider the extent. Of this solution curve along this y-axis. Okay. Y-axis also, it is nothing but a real line, right? Okay. This is R2. We are considering R2 here. That is xy plane. Okay. So this R2 is simply R cross R. So this R is nothing but this y-axis. Okay. So now, if I can find, definitely, it is always possible to find an interval an interval like CD where the value of yx will belong to. Is it okay? So basically your yx, if I assume that yx always lies in that interval CD, right? So then what is going to happen? Now I can definitely define a rectangle denoted by R like this. Okay, fine. So this is what you are going to get in all the initial value problem. They are always going to talk about a rectangular region R. Fine. So this is how it appears. Is it okay?
Yes, sir.
Yeah. So now, see, I'm going a bit slow today because these concepts I think you need to learn. I mean, very meticulously because I mean we maybe during MSc and BSc we used to memorize many of this stuff, but now coming to the real concept, you have to be very clear about your concept. Because see, why I am telling you this, like in your second year onwards, you are going to act as a teaching assistant. You got to tutor all our undergraduate students. So in that case, these concepts, I mean, you need to be explaining it to them very clearly. Okay, fine. So this is about that rectangle R. Okay. So now this is pretty straightforward for the first order, I mean, initial value problem. But in case of second order initial value problem, like say, had it been something like your d2y dx2, this is equal to f x y y prime. Of course, then it would have come up with, I mean, come up with two initial conditions. That is, you would have been giving the first year also. I mean, they're giving a condition in terms of the first order derivative at that particular point x naught. Okay, so the geometrical interpretation is the same, except that now you have this extra condition. So can you tell me what that extra condition means? Yes? You're not getting it?
Sir, we
Yes?
have to find
You
one solution y equal to y of x which satisfies both conditions.
No. But what does that condition y prime x naught equal to y1 means?
So it is the slope at point x naught.
Exactly. We are seeking a solution curve in such a way that at the point x naught y naught, the slope of the tangent to the curve at that point is given by y1. That's it. As easy as that. Is it okay? Fine. So this is the geometrical interpretation of your this first order. So this is what it is. This is pretty straightforward. See, here you can see that the solution there in the shaded blue portion over there, and then you can see that, I mean, that is the interval I, okay, along x-axis, and they are showing some different curves there. But you can see that only one of those curves, I mean, it is passing through the point x naught y naught. So that is probably, I'm still saying that is probably the solution curve because it seems to fit the initial condition. Is it okay? Fine. So similarly, I mean, if I am talking about a second order ODE with these two conditions, so then as I have told you, that is simply going to represent the slope of the tangent to the curve, the second condition to be precise at that particular point. Fine. So first of all, okay, fine. So like let me just show you some example. I mean, what is the solution of this equation? Forget about those points. Yes?
Sir, e to the power x.
E to the power x. Okay? So we are seeking solution. We are seeking solution in such a way that like your y0 equal to 3 and then y1 equal to -2. The solution is e to the power x here, that's fine, but it will be something like that, c e to the power x, okay? Because if I plug in y equal to 1, then e to the power x is always going to give me, what? It is always going to give me 1, right? So basically for this, the solution will be y 3 e to the power x, and for this, what it will be?
minus 2y
Minus
2y minus 2 e to the power x minus 1
e to the power
x minus 1.
yes, good. Yes. Okay, fine. Or simply you can you can adjust simply something like this, 2 by d. Fine, something like that. Okay. So basically what we are seeking these two curves passing through the point in the first case 0, 3, and in the second case 1 minus 2. And in your slides now you are going to see how they look like. Okay. How they look like. Okay, fine. So now you can see that corresponding to different values of c, you can see some curves like c to the power x, and you can see that here only two of those curves are passing through these two specified points. Fine. Okay. So in my next slide, I'm going to ask you some questions. So be ready for that. Yeah. You may be thinking that I have chosen these three examples randomly. See, here I'm talking about three initial value problems, right? Represented by a first order differential equation. Okay. Now you can see in all the cases the right hand sides are different. Fine. In all the cases the right hand side are different. Okay. And now, can you tell me, what is the purpose of, showing you these three particular examples?
I think, sir, you want to know about the which functions will be has solution or not, and if some function has some solution, how many solutions will there?
Yes, you got it. You got it. Thank you, and I really appreciate that. Okay, so in the first case, your dy dx that is equal to 1 by x, and then your y0 equal to 0, right? Okay, so now can you find a solution to this? This differential equation.
No, sir.
Why?
Sir, actually, if I find the general solution, we will get the term log x, but log x is undefined at the point x equal to 0.
Okay, that is one possibility. See, okay, that's fine. Either, in order to check it, either you go for a general solution or you seek a constant solution, right? Isn't it?
Yes.
I can seek a constant solution also. But here you will see that even if you try to seek a constant solution, that is also going to fail because you are going to get 1 by x equal to 0. Isn't it? You are going to get something like that. You are going to get something like that. And that is going to lead you, nowhere. Fine? So basically, this example tells you that it has no solution. Okay?
Sir, 1 by x is unbounded near 0, in the neighborhood of 0. Near to 0.
Yeah.
So this is the big problem in this problem.
No, that is where the problem is, right? So this equation, doesn't possess a solution. This initial value problem has no solutions.
Yes, yes.
Okay, fine. So now let us consider the next one. dy dx equal to mod of 1 minus 1 and y0 equal to 1. Y0 equal to 1. Okay, and here, like say, what it is saying is that either, say, mod of y minus 1, that is going to be a non-negative number, right? Is it okay?
Yes, sir.
Yeah, it has to be. Like, don't hesitate. I mean, you don't think that I'm looking for a hi-fi answer. This is as straightforward as that. So, like say it is non-negative. So that means if you are visualizing the curve, if you are visualizing the solution curve, you have to visualize about a curve, I mean, where the slope is non-negative. So that means either it is a monotonically increasing curve or what?
It will be monotonically increasing as it is positive, dy by dx is positive.
No, that is fine. I'm telling you, I'm asking you, either it is monotonically increasing or
Constant.
exactly constant. Okay,
Yeah.
I have given you enough hints. So now tell me, what kind of solution are you going to get here? Under the prescribed initial condition.
Sir, y equal to 1, y of x equal to 1.
Okay. Firstly, does it satisfy the differential equation?
Yes, sir.
Yes. Okay. Fine. Obviously, this is a solution of the differential equation, and of course, because this is a constant function, if for any value of x, I'm going to get the value 1. So even for 0 also it is going to work. Fine. So what about other solutions? Can you get some other solutions? Can you think about any other solutions? Yes.
Sir, 1 plus e to the power x.
1 plus
Sorry.
for x.
1 plus, sorry, it will be not 1.
Okay, let me guarantee you that you won't be able to find any other solution. Okay, so that means this has only one and only one solution. Fine. So that is what we call it as unique. Okay. And what about the third one? Third one, you, I mean, like say, you must have been very comfortable with that one. I have been using that repeatedly. Looks like it's a very.
Sir, how can we say it has no other solutions other than?
You try to find out, then I can, or you give me. I am telling you, I am guaranteeing you. So you have to give me the reason why it cannot have any other solution than that. And
Yeah.
that will come from the solution curve. Let me tell you.
Okay.
Okay, whenever you try to visualize the solution curve, you cannot get whatever is the differential equation. From there, you cannot get anything other than that. Anything other than that. Okay.
Okay, sir.
Oh, so if you plug in any other value, so whether you are going to get an answer to that or not, you please, and this is a homework also, you please think about it. Okay, and this is very interesting and very simple also. Okay, so now, does this ring a bell? You remember, I mean, this has a solution like something like 16x to the power 4, right? And in fact, we got, I mean, the family of solutions like 1 by 4 x squared plus c whole squared. So these gave me the one parameter solution of curves, right? Okay. So, and from here, if I plug in c equal to 0, definitely I'm going to get 1 by 4 x to the power 4 as my solution. Okay. and then that is going to look like that and it is going to look something like, sorry, it is going to be a flat curve. Here it is going to be a flat curve. So this is y equal to x to the power 4 by 16, say. Okay, and then I already yesterday we discussed that it is a singular solution y equal to 0 also, isn't it? Fine.
Yes, sir.
So now this is this blue line will be y equal to 0, and then you can see that what is the initial condition? Any solution curve has to pass through the point 0, 0. So now here you can see that I have got two. Right, I have got two curves passing through the same point, and obviously this family of solutions, even if this was absent from this itself, you can say that it has an infinite number of solutions. Is it okay? Fine. So I have presented you with three scenarios. In the first case, it doesn't have any solution. In the second case, it has only one and only one solution, that is unique solution. And in the third case, it has infinite number of solutions. Okay. So that brings me to the question, like say, under what circumstances these three different conditions, are possible. Okay. So that is where the answer is going to be given by, for this kind of, first order ODE, the answer is going to be given by Picard's theorem, uniqueness and existence theorem. Okay, so in my next slide, I'm going to show you the theorem, and then I'm going to again discuss some relevant topics, connected to that. And probably only tomorrow, I'll be able to touch upon the exact proof of this uniqueness and existence theorem. So before that, let me see what is. So this I have already shown it to you. So now this is the question. There are two fundamental questions associated with the above three differential equations. So what are that? Does a solution of the problem exist? Okay, so that is related to the first two differential equations here. And if a solution exists, is it unique? Now from there, from all three, you can see that from the second and third one, you can see only the second one possesses a unique solution. Okay, so in order for seeking the answer, we can be more specific about this existence. Does the differential equation dy dx equal to f of xy possess a solution? If at all, if it possesses a solution, do any of the solution curves pass through the point x naught, y naught? Okay. And what about the uniqueness? When can we be certain that there is precisely only one solution curve passing through that particular point, x naught, y naught? Okay. And these answers, okay, so rectangular region I have already explained. This one I have already explained how you come across this and where the concept of the rectangular region coming from. I have already explained it to you. See why this rectangular region again, because you will see that in the uniqueness and existence theorem, they are going to talk about this rectangular region. So that is why this has been roped in. So I have pattern pasted from somewhere else, like say, basically I'm going to follow the Simon's book, and it is the same statement, but maybe in some different shape they are going to tell it. Don't worry about this. Okay. So if f is f is continuous on an open rectangle. So see, don't need to worry about this open rectangle, closed rectangle. So basically, if a rectangle is formed by the that cross product of two open intervals, we are going to call it an open rectangle. So basically, we are not going to consider the points belonging to the what?
boundary of the closed rectangle.
Yeah, basically the sides of the rectangle. Okay, fine. So if f is continuous on an open rectangle defined by that, you have that. Okay, that contains the point x naught y naught. Okay, then the initial value problem given by the equation 2.3.1, I'll write it down, don't worry, has at least one solution in some open subinterval of AB that contains x naught. Okay, and that is about the existence. Okay, now secondly, if both f and partial derivative of f with respect to y, if both of them are continuous on that open rectangle R, then it has a unique solution on some open subinterval of AB that contains x naught. Okay, fine. And please don't be afraid. Like say we have some kind of stigma. I mean, we have some mental blockade that, oh my God, this subrectangle subset. We tend to think that, oh my God, I am an applied mathematician. It has come from pure mathematics concept. Don't think like that. Mathematics is mathematics. Okay, and it is pretty straightforward. You just get rid of that mental blockade, and then you'll be fine with that. Okay. So now let me try to explain about that open subinterval part. Okay. So how you can get rid of all that mental stigma. Okay. Fine. So I'm looking for a yellowish one. Okay. So let me predetermine this. Okay. It could be. Okay. Let this look like a rectangle, not a square. So suppose this is x, this is y, and this is A, this is B, this is C, this is D. Okay, and here are the, and again, see, different books, they are going to use different symbols. Don't worry about it. Okay, so this is like say what is R? R, it contains points like x, y in R2, right? In such a way that x strictly lies between A and B, and y strictly lies between C and D. That's it. You don't need to worry that much about it. Okay. So don't be afraid that I'm looking at this kind of stuff. Well, it is mathematics stuff. It is not pure mathematics or applied mathematics. Okay, fine. So then, I mean, this is the, I mean, bearing the, I mean, sides or boundaries. So this is my R. Okay. Remember, this is not real line. This is simply R, a rectangle. Okay. So then I have been given some point x naught. Okay. Now I am seeking a solution. I am seeking a solution, something like that, something like that. So passing through the point x naught y naught. Is it okay? Fine. So far so good. Now remember one thing. I mean they are talking about a rectangle. They are talking about a rectangle. Okay. Now if you are going to consider a curve which lies in the rectangle, the curve can have, I mean, infinite extent. It, not can have, it already has an infinite extent. Okay, like you may think that I'm going to consider only this much of the curve, right? But what is going to happen? This much of the curve also, it has an infinite number of points. Is it okay? Fine. Now remember, like whenever you are going to be given an initial condition, it is going to consist of only one point belonging to some interval on x-axis. Is it okay with everybody?
Yes, sir.
Yes, sir.
Yes. So that is why we are interested only, remember, because I have been given only one point along x-axis in a certain interval. That is why I'll be interested on the solution curve only in the neighborhood of the point x naught. Is it okay? Fine. I'll be interested only in the neighborhood of that point x naught. Okay. So that is where what we are going to do later on also during the proof of these theorems. You will see that I am going to talk about a sum-interval defined by this where h is a positive number, very small, however small, something like this. Is it okay? So basically, what I'm seeking x to be lying in this interval. Okay, fine. And see, they are talking about an open sub-interval, but here I can simply take a, so from the inequality, you can see that I can even take a closed interval also, closed sub-interval also, no problem about that. So basically, that sub-interval they are talking about, it is going to be something like what I used. Okay. It is going to be something like this. This is x naught minus 6. This is x naught plus 6. Okay. And apart from this, let me tell you beforehand what they are going to do. So now you see what is happening here. Can I use some other color? Just give me a second. So now you can see that in this sub-interval, my extent of the solution curve is something like this. Okay. Can you distinctly see the color here?
No, it's same.
Yeah, is it obvious that? Anyway, I think you are getting it. So this is the portion of the curve, solution curve in the whole interval AB, which belongs to the sub-interval x naught minus h comma x naught plus h. Okay, fine. So similarly, what I can do now, because the extent of my curve it has become smaller, so now I can again choose something like a sub-interval along y-axis, right? So, like say maybe I can choose something like what was the point? Okay, so suppose this is the point. I can choose something like, isn't it? Which will be defined by y minus y naught less than equal to ksa. Fine? Okay? So now what I am coming to. So that is going to form what is happening here? That is going to form another rectangular region which is the subset of the original rectangle R. So in Simon's book, they are going to define it as a subrectangle R prime. So this is why I am telling you, I am giving you the information beforehand, because later on, when I am going to discuss all this stuff, so basically you have to assume that I am doing something like this. Is it okay with everybody? Fine? Okay. And again, see, when you again go through all these things that I have taught in class, please try to draw the things on your own. You will see that whenever you try to draw something or you try to visualize, your concepts will become more clear. Okay, fine. So, this is fine. As I have told you, A is an existence theorem. I don't want to ponder much over that. I have already told you that I am simply seeking some solution in the neighborhood of x naught. And whenever I am not talking about a unique solution, so it may so happen that there may be more than one solution curve passing through the same point. Okay, fine. Now this is very interesting. Can you, like I'm giving you 1 minute or so, can you just have a look at that? Can you just have a look at what is written there about this uniqueness. I'll try to explain it to you. In fact, we are going to work out some problems later on. Once we have proved uniqueness and existence theorem, so we are going to do something like that. Okay, so have you gone through it? Have you gone through it, or you're still trying to understand it? See, what they are saying is that, say, suppose I am considering a solution of a given differential equation, or to be precise, I am considering a solution curve yx of a given differential equation. In that, say, they are talking about open interval. I found it that. So suppose in this open interval AB. So now, if you look at my graph here, see, I have drawn a yellowish curve in the interval AB. Okay, and again, they don't talk about okay, any initial condition. Okay, there may be some initial conditions. Suppose this is x naught y naught. Okay, so now what they are saying is that, say, suppose your b1 is greater than b. Suppose b1 is greater than b. So the way I have taken it here, right? So then it may so happen that in the interval, I mean a comma b, you are having a unique solution, right? But if I consider the extended interval a comma b1, you may not have a unique solution, because you may have then your branching out at this point. That is what they are saying, right? So that means you may have a solution curve in the entire interval a comma b1, like, say, given by this pink curve, and another solution curve given by the blue curve, where suppose I am calling this as y2x, and suppose I am calling this as y1x, and these solutions are such that your y1b equal to y2b. Are you getting that thing? Whatever is written there? Now is it clear?
Yes, sir.
Right? That is what they are talking about. Like, say, this is the situation. So this is the situation. So now it seems that if you have a situation like this, then the condition, say, definitely if f is continuous, a solution exists, right? Whenever we are talking about these differential equations. Okay. Now, if both f and fy both are continuous, of course, in that open rectangle R, so then it guarantees me a unique solution. Okay. So that means Probably, I'm not saying with full confidence, because only after I prove the theorems, and then after that we work out certain examples, only then I will tell you that I'm extremely confident, and yes. But now I'm going to say, because I still haven't proved it, that probably, because we have already seen that the solution exists, okay, but since it is not unique, so probably the second condition, that partial derivative of f with respect to y has to be continuous, probably that is not satisfied there. Is it okay? Fine. So these are the things we will try to find answer to. And you may be thinking why we are why we are trying to do this kind of uniqueness and existence theorem, because we already know, method of separation of variable, homogeneous function, blah blah blah, lots of techniques, but the theory is important. You got to ask yourself the question, if at all, whether the solution exists, even if it exists, whether it is unique or not, and if it is not unique in a certain interval, why does that happen? Okay, so we'll try to figure out all those stuff. Okay, so that brings me to the end of the first part of today's video. So maybe I will sip some water. So now, again, let us come to now method of successive approximations. Okay, so now you may have done it before, and you saw that, oh my God, it is so easy. Like we are trying to generate a sequence through some formula. y0, y1, y2 up to yn, and then it is fine. Like in your exam, you got to find, up to 3 terms, and then you have to check whether it agrees with the solution of the given differential equation or not, right? This is what you did, right? Nobody is answering.
Yes, sir.
Yes, sir. This is what you did. Now, because now you are PhD students, now you have to become more mature. You have to know why we are studying this, okay? And in India, I have found out that the students, don't ask that many questions. Like they're happy. Whatever the professor, teaches them, they're happy with that, because most of them are worried only about the numbers that you have to get in your exam. But in other countries, like say I have taught in US also, there, before embarking onto something, the students are going to ask you that why are we doing this? Okay, so you've got to ask me, why are we doing this? So I'll try to answer that. Okay, fine. Let me tell you what we are going to do here. So it is method of successive approximation, and of course it is by Picard. It is by Picard. Okay. So in fact it is Picard's method of successive approximation. Okay, fine. So what does it do? See, this is my initial problem. Okay, so let me tell you that, okay, I am seeking the solution in some neighborhood of x now. Okay, fine. So now the existence of uniqueness theorem, it tells you that if number 1, f is continuous, a solution exists. Okay, and number 2, if both are continuous, that the solution that exists, it is unique. Okay, so that means you will get only one and only curve passing through the point x0, y0 in the neighborhood of x0. That's it. Okay, so now we have to prove it. But the proof is not that straightforward. Okay, but you will see that the way Picard has generated a sequence, from that sequence you will be able to prove, although I'm saying that it is not that easy, but you would be able to prove it smoothly. Okay. So what Picard did, he looked for some alternative definition. Now, what that alternative definition is, so he was trying to find the solution of this in terms of an integral equation. So what is that? Like say he was trying to find a solution in terms of something like this. Okay, fine. Now, see, this is my problem, and this is an integral equation, which is giving me an expression for the assumed solution yx in terms of an integral equation. Is it okay with everybody? Fine. Okay.
Yes.
In fact, Picard was trying to find an equivalence between yx is a solution of this and yx is a solution of this. Okay. Now, one thing you have to remember. See, here, this part, this integration, this definite integral over over that, what should I say, variable interval x naught comma x, isn't it? Because depending upon the value of x, the interval is going to, interval will keep on changing, right? Extent of the interval. Okay. Here, one thing you have to remember that many a times over, when you are going to read the book, you will find that they are talking about continuity. Why they are talking about continuity? Because even say, and they are talking about the function, they are talking about this function being continuous in the interval of definition. Okay, why it is so? All the time they are saying it. Let me tell you that the first thing is that without continuity, you are not going to get differentiability. And in order for the construction of the differential equation, we must have differentiability at least up to first order, because this is the first order differential equation, right? That is why continuity is definitely required. And in the second case, why they are talking about it more is that this being an integral expression, you know that from Riemann's theory, that even if you have a finite number of discontinuities for a function, you can always evaluate a definite integral. Is it okay? Fine. So that is why they will be constantly talking about the continuity of the function. Okay. So now let us see whether the yx as a solution of this and this, it is going to give me the same thing or not. Okay. So, and that is pretty straightforward. Let me tell you. Like so. This is my given differential equation. Okay, so now if I integrate this relation, between the points x naught and x, dy dx, and here what I'm going to do, I'm simply going to use dummy variable, like say and of course y, sorry, not x, this is yt dt, right? Now if you integrate it, this is going to simply give you yx, right? Okay, or maybe what we can do, let me use dummy variable for this also, then it will make more sense. Okay, so then this is going to give me yt x naught x, and this is equal to x naught x f t yt dt. Okay, and from here you can see that this is going to give you yx minus yx naught, right? And you know that yx naught is nothing but this initial condition. Okay, fine. So from here I will have got yx to be equal to y naught plus x naught to x f of t yt dt. Okay, so that means if I call this integral equation as 2, that means 1 and 2 are equivalent. Is it okay with everybody?
Yes,
right?
sir.
Okay.
Yes, sir.
So that means now let us come to generating a sequence part. So that means if somehow I can find a yx, I can find a continuous function yx in terms of this, my job will be done. So for this, what Picard did, because he was not directly able to find the yx. So he was thinking, why don't I try to generate a sequence of functions? Okay. Now, after generating the sequence of function, if I can prove that that sequence of function is somehow convergent, of course, being a sequence of function, it is definitely, if it is convergent, it is going to converge to a function. Okay. Now, if I can find a function, I mean, which belongs to that, I mean, subrectangle, or which belongs to a rectangle in the neighborhood of the point x0, y0, my job will be done. Okay? And if I can show that the limit of this sequence is nothing but the solution of the given differential equation, then my job is done. So that is why Picard has, I mean, brought on the idea of generating a sequence. So that is where the Picard's method of successive approximation comes into picture. Okay, so this is the history. Like, I mean, I think I have Picard's. So this I have already told you. This is fine. I have given you enough explanation for this. So I have a historical note on Picard. That is why I was trying to. Okay, fine. So now let me come to the generation of the sequence part, and it is also very interesting. So firstly, you've got to believe that those expressions 1 and 2, those equations 1 and 2, they are equivalent. One is going to lead to the other and vice versa. Okay, fine. So now, okay, let me firstly draw the figure. Something like this. Okay, and suppose this is my open rectangle, this is R. Okay, so this is the point X. This should be good enough. This should be good enough. Okay, fine. Now, you know, like say, what my aim is, I am trying to find this curve, this green curve passing through the point x0, y0. Okay, fine. Now, I am trying to generate this through a sequence of functions. So basically what I am trying to do, I am trying to find some, say each sequence, say suppose I am trying to generate sequence of functions like this. And so on, right? So each of these I mean, members belong to the sequence, it is going to generate a curve, isn't it? So basically, what is happening? We are trying to generate a sequence of curve passing through, say, this point, passing through this point. Okay. So I am trying to generate them in such a way that eventually, if this sequence, I mean, converges to some function phi of x, that is nothing but the solution. That is nothing but the green curve. Is it okay now? You should know what we are trying to get. Fine. So in order to do that, what Picard did, that since I already have this initial condition, why not choose y0 x, this to be simply equal to y0. See, although I am using the same symbol, see, this is a function. So that means it is going to give me a solution. It is going to give me a curve, not solution curve. It is going to give me a curve. Okay. Now, can you tell me that my first approximation of the curve is what?
Constant function y0. Constant function y0.
So that means it is simply a straight line.
Yes.
Right? My first approximation, see, this is my first approximation. So this is my y naught x. Now, is it clear? My first approximation is given by this curve because this length is y naught. Is it okay with everybody? Fine. You should try to visualize it, not simply memorize. Okay? Fine. So this is my first approximation. So then you will see that sometimes back we were talking about those two equivalent expressions. The second expression from the second expression, what he did, once you have the expression for this, now the second member in the sequence, what you can do, you can define it to be this f t, then y naught t dt. So what does it tell you? So basically, if you say, suppose f of xy, suppose f of xy was something like x squared plus sine y. Okay, so in this particular case, it would have become something like okay, fine. It would have become something like, say, f e y naught t. So for t it is t squared and sine, because y naught x, so this will be simply y naught constant. Is it okay? Fine. So this is going to give you the first one. So now, so this is y1 x. So now from here you know that this is going to give you a function of x. Okay. So I get the second member in my sequence. So the third member, it will be again your y naught plus x naught x f t. Now I am going to plug this in y1 t dt. Okay, so in this way it is going to generate a sequence, and eventually the nth member of the sequence is going to be given by y naught plus x naught x f t dt. Okay, so this is what we can see. Fine. So this way we will try to go on improving my approximations one by one, and eventually what is going to happen, we will later on prove that this sequence is going to converge to the solution of the given differential equation. That's what we are going to do. Okay, fine. So now let us just take one example, which probably you did earlier. I'll do one more. So is the thing clear now? What we are trying to do?
Yes.
Yes.
So we are simply trying to generate a sequence, which we are later going to prove that in fact is not only convergent, it is uniformly convergent. I'll talk about that also. Uniformly convergent, and the limit of this sequence is nothing but the solution of the given differential equation. And under those prescribed condition, this solution is going to be unique. Okay. So now, let's simply take a very, you know that here, I mean, y equal to e to the power x is the solution, right? This is y1. So now, see what is being given, y not equal to 1. So basically here, x not equal to 0. Fine. So then, in this, so it will be simply 0 to x f of t y n minus 1 t dt, right? So now, what is going to be your y1x? Because say your y naught x is simply 1. Right? The very first approximation we take it from the initial condition. So this is going to be y naught. Y naught was 1 plus 0 to x. So f of t, and this is simply 1 dt. Is it okay? Fine. And here, see, here what is happening? Your f of xy is simply y, isn't it? Fine. So what we are going to do? What we are going to do here? So this is my here. The value of the second coordinate is 1. So here you can see f of xy is equal to y. So here simply 1 dt. Is it okay? So y1x equal to 1 plus x. Fine. So then now your y2x. So this is again equal to y naught. This is 1 plus 0 to 1 f of t. And then what is y1t? This is simply 1 plus t. Is it okay? Fine. So, and again, f of xy is y. So only this component will come. So it is 1 plus 0 to 1. 1 plus t dt. Okay, so this is going to give you 1 plus x squared by 2. Okay, so in this way, if you go on integrating through this formula, then you will see that as n tends to infinity, this series eventually is going to lead you to the power x. Fine. So that is the way we are going to proceed. So maybe at the time, maybe in tomorrow's class, we are going to work out one more example, and then tomorrow I'm going to talk about uniform convergence and what is the significance of uniform convergence in terms of the proof of the Picard's uniqueness and existence theorem that I'm going to explain. And only after that, we are going to formally embark into solving uniqueness and existence theorem. And please don't think that, oh my God, we are taking so much time trying to understand only one concept. No, we should give time. Like say, let me tell you one thing. This is about construction. This is about constructing the proof. Sometimes you will see that, like say in some of the proofs of some theorems, you can get the proof through only 1 or 2 lines. But in some cases, in order to arrive at that, you need the help of so many different things. And those things, sometimes they come in terms of some lemma, right? You will have so many lemmas, and only after that the main theorem will come, right? So although we are not going to use any lemma as such, because I'm going to start from scratch. Okay, so it is like if you, follow some sports, then in cricket, you can win a match by simply hitting a 6 in one ball, right? But in order to get the winning score, sometimes you may have to struggle. Okay, so that is what it is about, constructing the proof. Okay, so that's what we are going to do in my tomorrow's class. So I will stop it here. So I'll see you tomorrow. And again, before we leave, let me tell you that probably I'm going to have your first quiz on September 19th, the Saturday. Not this next Saturday, the Saturday after the next Saturday. Okay, 19th September. And I'll tell you how I am going to work it out. Okay, so what is going to be the modus operandi in conducting the exam? I'm going to tell you. So I'll let you know beforehand. Don't worry about it. Okay, so then I will see you tomorrow. Okay, bye for today.